right, so THERMOCAL stands for Thermophysical Properties of Caledonian Rock Materials to De-risk Geothermal Development. I'm presenting to you today in my capacity as the principal investigator for the project, but really I'm presenting on behalf of the entire THERMOCAL team, which I'm going to introduce to you in 1 second. I'm also going to introduce shortly the various partners that we have on the project. So for today, I'm going to give you just an overview of THERMOCAL. Really, we don't have time for great technical dive-ins, but hopefully you will walk away from this conversation today with an understanding of what the project is, what the project aims to do. So I will introduce the team, the context and the vision of THERMOCAL, the expected deliverables and the structure of the project. I will then give you snapshots of the individual work packages in THERMOCAL, and most importantly, I will show you how you and everyone out there can engage with us and with the project. So THERMOCAL has been funded by the Engineering and Physical Sciences Research Council here in the UK, but that has happened through a particular program. It's called the Money Follows Cooperation Agreement between UKRI here in the UK and the Research Council of Norway. So that was an amazing opportunity for us to join forces with colleagues in Norway, and so we have an enlarged team. As you can see in the middle column there, we have the University of Glasgow team, with Glasgow being the lead institution. That's myself, joined by Dave Banks, Sean Watson, Isa Colo, and PhD candidate Alex Comerford. We also have colleagues at the Norwegian University of Science and Technology, that's Bjorn and Randi. We have colleagues at the NGU, the Geological Survey of Norway, Marco, Claudia, and Trond. And then we have colleagues at Queen's University Belfast, that's the team led by Ulrich, and we have research fellow Mahmoud. And last but not least, we also have SWERG with representation given by Alan Cresswell and Tristan. Tristan has effectively just joined us today. On the right-hand side, you see the happy team. There was a team photo of us taken in our first field trip under the umbrella of THERMOCAL in August last year. In addition to the researchers team, we also have the support of external partners. They're shown on this slide. We have the European Geothermal Energy Council, of which the University of Glasgow is a member. We have the British Geological Survey, the Geological Survey on Northern Ireland. And then on the right, you see two companies represented, two industrial representation flags, Town Rock Energy and Eden Geothermal. And last but not least, again, latest news are that we have already the pre-approval from UKRI to include GFZ, the research center for the subsurface for geosciences in Germany. And that's going to be represented by Dr. Sven Fuchs. So we're very pleased with this support that we have received, and that is real support. It's support that we obtain not only in the context of writing the application for funding, but also already since the start of the program, we liaise with our partners, we receive advice on all aspects of the project. So the context that led to the submission of the THERMOCAL funding application and the vision of THERMOCAL, it is clear that all three participating nations, that is Northern Ireland, Norway and Scotland, have very large ambitions for geothermal technology. Problem is, or let's say the opportunity is, how to translate the ambition into reality. The UK and Norway share a continuous Caledonian terrain all the way from Northern Ireland through Scotland to Norway, and an extensive set of areas of hard rock lithology. At the moment, the main form in which geothermal energy is being exploited in the three nations is via relatively shallow ground source pump systems. And typically, those are coupled to closed-loop borehole heat exchangers. The THERMOCAL vision is to carry out a systematic measurement program with unified sampling and analytical methodologies of the lithologies in the Caledonian terrain across northern UK and Norway. We will complement that with bespoke modeling approaches to translate the subsurface potential into something more realistic by means of project interpretation. How do you actually construct the systems that will tap the thermal potential and translate into a usable product at the surface? So we really want to investigate the impact of data on real-world geothermal engineering applications, and that will be both for shallow applications and deep applications. I mentioned the ground source heat pump installations. On the left, you see two maps extracted from the microgeneration certification scheme data dashboard available online. And of course, it's clear that not all ground source heat pump installations are MCS certified, but the majority is. So the maps here probably represent a slight underestimation of the number of installations present today. Nevertheless, as of September 2025, based on the information, we can say that we have a total of 3,720 installations in Scotland, 387 in Northern Ireland. In Norway, there are 55,000 estimated installations of ground source heat pump systems coupled with closed-loop borehole heat exchangers, and they contribute to about 4% of the national heating demand of Norway. Deeper geothermal prospects are certainly being considered as a viable source of low-carbon heating too in each of these three nations, but today, as I speak, we still do not have active deep geothermal systems in these three nations. How is the project structured? It's structured in work packages, as most research projects are. I will go through each of those work packages in a little bit more of detail in the remainder of the presentation. But above all, the overall aim is to come up with a public, representative, and quality-assured database of the thermal and radiogenic properties of the lithologies of the Caledonian Orogenic belt. So those keywords are all very important. It's public data. They need to be representative for the scope and the aim of geothermal development. They need to be quality assured, and we want to encompass strategic thermophysical properties of rocks relevant to geothermal resources. The issues that are emerging are already very interesting, and I will go through them as I go through the work packages. So, except for project management coordination, which is the usual joyful challenge of coordinating technical work, but also interfaces with all stakeholders and making sure that we are reporting regularly, keeping an eye on our finances for the project, etc., etc. So excluding work package 1, which is probably not terribly interesting, I'm going to go through the other work packages now. So let's start with work package 2. That work package is on data compilation and analysis. It aims to compile systematically all data which already exists, all data on thermal conductivity, volumetric heat capacity, and radiogenic heat production in Scotland, Northern Ireland, and Norway for the relevant formations. That's not a slim challenge because there is certainly quite a bit of information out there in very different formats, as you can imagine. Some data are relatively old, some data do exist, but we then need to assess later in the other work package whether they are fully reliable with the knowledge that we have today. As Dave Banks likes to point out very regularly, the idea is not entirely new. There is a publication that dates back to 1882, which is indeed aiming at doing exactly the same. But we can fast forward in 2026, and THERMOCAL is trying to bring together the data of today for the specific formations. On the right, again, another happy picture of us in sunny Scotland in August 2025, led by Dave marching forward, and everyone else was struggling to keep the pace of his walking. Ongoing work in WP2, we have already made good progress with data compilation and quality control. We have already prepared a manuscript on existing thermal conductivity and volumetric heat capacities for the Caledonian terrain in Scotland, Northern Ireland, and that was submitted to the Scottish Journal of Geology. We are also preparing a paper on thermal conductivity data from laboratory and from in situ measurements in Norway. And there's a third paper in preparation, which is on existing radiogenic heat production in Scotland and Northern Ireland. Excuse me. And the picture you see on the right-hand side is a courtesy of Bjorn in our team. It's a very, very nice sample of Central Highland metamorphic rocks. And we took it during the field trip as well. Just to give you an idea of some of the things which have been emerging through the review that we've been carrying out already in THERMOCAL, we've got two pictures here. So one is showing, the thermal conductivities measured for Devonian sedimentary rocks from the Orcadian Basin and the Midland Valley. And you see already a good spread of numerical values there. On the right-hand side, you see something more thought-provoking. It's the effect of anisotropy, and that is for samples which had a clear foliation present. So depending on whether you take the measurements parallel to the foliation or perpendicular to the foliation, there is a difference in the resulting measured thermal conductivity. And that is not trivial, because we are dealing with anisotropy in the context of geothermal developments, and so this is something that definitely deserves being explored further. Let me move on to work package 3, which has a delicate task of carrying out quality assurance of the data, but also harmonization of how we acquire the data. So you can imagine there is an aspect of making sense to data that already exists from the past. How were they collected? How were the measurements carried out? How were the results analyzed and interpreted? Then there is the challenge of acquiring new data, which is not just about walking out there and taking any sample, but it's about understanding where we need to go, what we need to gather, and what we need to measure. So to do that, we started by deciding that we wanted to have 2 team field trips aiming specifically at identifying subsequent testing sites for the project. We did one field trip already, as I mentioned earlier, and that was in Scotland last August. And we're going to have another one in September in Norway this time. So we have pre-identified areas for the field trips where the team is coming together not to actively and extensively collect samples or take measurements on site, but rather to process how we want to do things as a team. What do we want to do, where, in which order, in which sequence? For example, if we collect samples in Norway, how do we then repeat measurements at potentially different locations? Do we want to do measurements of different samples in parallel, or do we want to take the same sample across different labs? Of course, I haven't talked about the labs yet, and I haven't talked about the measurements we're planning to do yet, but that will come shortly. We also started to think about superimposing criteria for the sampling, and those should be not just geological criteria or heat flow criteria, but also criteria about access to the sites, criteria about closeness to heat demand today and in the future, criteria about, generally speaking, potential constraints that could be in nature reserves. So there is many layers that we are building together using GIS, for example. And we think that GIS can be very powerful also for presenting the final, some of the final results of THERMOCAL at the end of the project. Still on work package 3, as I mentioned already, these field trips have been very important to discuss how to carry out consistent sampling. how to adjust procedures also, and how to include not only sampling for measurements of, say, thermoconductivity in the lab, but also inclusion of gamma ray spectrometry and other measurements, which I will discuss in a second. We also wanted to start thinking about whether it's possible to standardize the way in which we collect and process the samples, the way in which we also capture the information and metadata on those samples. And we want to also consider locations where we can carry out new airborne gamma spectrometry in order to compare those results with information obtained from the sample scale. So this is now gradually bringing me to discuss additional measurements that we want to do. I've already just mentioned the airborne gamma ray spectrometry. We will also carry out gamma ray spectrometry with handheld devices, which we had prior availability of here at the University of Glasgow. And so we start now thinking about scales. We start thinking about scales of measurement and scales at which those thermophysical properties of the rocks introduced at the beginning of this conversation can or cannot be captured by these different scales of measurement, and how they can be reconciled at those different scales. In the field, we are going to perform comparative measurements of the same classified lithologies or outcrops using calibrated gamma spectrometry instrumentation. In the lab, we're going to be using reference material for which we know the values of their thermal properties, and those will be benchmarks for the quality assurance campaign before laboratory measurements carried out in the next work package. So next work package is work package 4, thermal parameters determination. It aims to collect representative samples from Caledonian rocks in the 3 nations in order to determine the thermal parameters. We plan to take approximately 200 samples from Norway and Scotland and about 100 samples from Northern Ireland. Of course, this might change, but that is the order of magnitude of the samples that we want to collect. The thermal parameters to be measured will include thermal conductivity, thermal diffusivity, which can also be derived, of course, from other measurements, specific heat capacity, and we will also measure density. The data will supplement existing data sets, so we want to make sure that we are not reinventing the wheel, that we are not unnecessarily wasting our resources, but there might be a need for repeated measurements where there are unresolved question marks. In collaboration with other work packages, we also want to consider the use of new instrumentation, and we want to test and develop best practices for future measurements in this space as well. This is a selection of the instrumentation that we have available to the consortium, but there is more than what I'm going to be presenting today. There is a newly purchased hot disk at NGU. It's the hot disk TPS 1000 for thermal conductivity measurements. It is equipped with both double-sided TPS and single-sided MTPS measurement options. It comes with a module for measuring anisotropy, which we said earlier is something we definitely want to explore in THERMOCAL, and certainly very important when working with rocks like schists and gneisses. We also have a hot cell as part of this package acquired by NGU, which provides independent measurements of specific capacities. And we have an oven to control temperature. Yes, and I should say obviously that the oven goes up to 300 Celsius, which is definitely more than enough for the range of installations and applications we're considering in THERMOCAL. Additionally, at the University of Glasgow, we've also placed an order for the portable electronic divided bar device, which is produced by Hot Dry Rocks in Australia. So it's going to come all the way from Australia. It's generation number 3 of this device that we are acquiring, and our colleagues at GFZ at the same time have ordered the same device. So we plan to do not only testing of how we can measure the same property with different methods, but also testing of repeatability of the measurement with the same instrument at different laboratory locations, just to see if there is any effect of that in its own. Work package 5 is also about measurements, but this time it's about RHP determination, radiogenic heat production determination. I'm sure I'm talking to an audience that doesn't need to be reminded of what radioactive heat production is, but just in summary, it's of course a petrophysical property that quantifies the amount of heat produced by the decay of radioactive isotopes within the rocks and the minerals. It's a function of the amount of potassium, uranium, and thorium present in the rocks, and the gamma ray spectroscopy allows determination of these concentrations of selected radioelements. We plan to also, should I mention earlier, we plan to also crush some of the samples and take direct measurements of potassium, uranium, and thorium that way. So as you can see, for every thermophysical property, wherever we can, we try to take different measurement approaches and then compare them, noticing also that some of these approaches do not cover the same scale. So let's talk a little bit about one of the core aspects of THERMOCAL scales. And I'm sorry if I'm insisting on it, but it's very important in order to bridge the gap that takes us from pure research to ultimate implementation of geothermal projects. So we have the scales involved across the entire project, and specifically when talking about RHP determination, we have the regional scale, where we can rely on measurements given, for example, by airborne radiometric surveys. We have the local scale, where we can rely on ground-based radiometric surveys. And then we also have site-specific scales. This is where we would be looking, for example, at downhole radiometric surveys and borehole logging. Let me go through these scales now, one slide each. For the regional scale, in Northern Ireland, our colleagues present in the call today will be very familiar with TELUS and the TELUS border surveys. They included airborne geophysical surveys and also soil geochemical surveys, both shallow and deep. For the TELUS airborne radiometric survey, data were acquired at 200-meter line spacing, flying at a height of 56 meters, and data were collected every second. That information is something we want to leverage, and we have expertise within the consortium, thanks to the team represented directly by Ulrich, and thanks to our collaboration with the supporting partners in the country. We also have existing airborne radiometric surveys in Norway, and those were radiometric data acquired at 200-meter line spacing, flying at a height of 76 meters, sampling rate of 1 Hertz, and with the resolution of 50 meters. At SUEC, we also have extensive experience with airborne radiometrics, and there is already data that were acquired by the team at SUEC by means of a helicopter-mounted system. So we have a sodium iodide system that was developed at SUEC, which we plan to use again for small regional surveys in Scotland. And then coming to the local scale, I mentioned that we would like to use the handheld gamma ray spectrometer that we already had at the University of Glasgow. We sent it back to the manufacturer for recalibration, and we just received it back. So it's ready to go back in the field as soon as possible. And Sean and Alex will do so very soon in the next few weeks. We also have a backpack system available, developed by and also available as work. You can see on the right-hand side those preliminary measurements that Alan carried out when we went to Aviemore, to the north of Scotland. So while the geologists were enjoying the beauty of very small, tiny minerals, Alan was walking up and down, taking these initial measurements with his backpack on himself, carrying quite a bit of weight. So again, different type of measurement from handheld to backpack system to airborne surveys. And we also have access to site-specific information through, for example, spectral gamma ray logging in existing boreholes across formations in Northern Ireland and existing spectral gamma ray logging data at NGU. So we will be combining all of these. This is a challenge because we need to really understand the latest technology available today for the measurement of these rock properties. We also need to understand how measurements were taken in the past and in the previous past. Some of this data in some of the nations mentioned are quite old. We need to understand if the QCing was the same, most likely not. I suspect you already know the answer. So when we then go and create a mixed database, we're going to have to be very careful about whether we can really say that we can mix apples with apples, or rather apples with something else. So it's a very interesting and fascinating exercise that we're going to, and it's nice to have that specific geothermal focus in mind. Let me now move on to Work Package 6. Work Package 6 is what is going to then understand how all this data collection and interpretation campaign is or isn't going to make a difference to how we plan geothermal projects, and whether this way of acquiring new data, interpreting data, allows us to help the process of de-risking geothermal projects. So it's a very fundamental step that we have. This is a very significant work package for us, like all the other ones. We want to carry out scenario analysis in a virtual modeling environment in order to consider configurations that would otherwise be too difficult, too risky, and certainly very expensive to carry out straight away in the real world. So let's use this virtual platform in order to see how the data can influence decisions for shallow and deep geothermal development. This is an example of the workflow that we will follow, which is inspired by the workflow we previously applied in other projects, including the Integrate project that concluded just over a year ago. So these are workflow for numerical modeling of deep borehole heat exchangers, going all the way from development to validation and verification, and finally to applications. So we go from constructing a conceptual model to, if we go numerical, implementing meshing and discretization, then verification and validation. And of course, when we don't have raw data from a given site, we're going to have to use analog data where existing, where applicable. And then, of course, running the model and interpreting the results through analysis. Very similar workflow for thermal energy storage. You might wonder why I'm mentioning thermal energy storage now. Well, because of course we consider underground thermal energy storage to go hand in hand with geothermal. And we see that UTES, underground thermal energy storage, is really becoming prominent in national, international discussions, because without storage, we know already we are not going to debottleneck the issues around integrated and resilient energy systems, coupling the electricity vector and the thermal vector. So here is an example of how we applied this workflow to shallow and deep boreholes for thermal energy storage, and we have already published in this field. So here is an example of what can be done with data to help communities, to help decision makers, to help investors decide where it is suitable to go for certain geothermal technologies and hence for certain projects in those areas. So on the left here, you have the Scotland heat demand map. On the right-hand side, you have the published heat pump suitability dashboard. So we want to do something like this specifically for the terranes of interest to THERMOCAL and for the three nations, and looking at not just heat pumps, but also something more than heat pumps, something deeper than heat pumps too. Considerations to keep in mind for us are listed here. We, as I mentioned before, definitely know upfront that we want to consider and investigate the effect of rock anisotropy, not just at the lab scale, but also overall on geothermal potential and thermal output from real projects. We know that there will be a need to couple the subsurface model with surface heat pump models in a whole system approach, because most of the applications will not have enough temperature to go standalone without the support of heat pumps. As I just mentioned in the previous slide, we want to consider the suitability of deep, shallow, and mid-depth systems within Caledonian terranes. We want to look at both closed-loop and open-loop systems in principle, even though in certain areas open-loop might not be possible. But Caledonian terranes include not only the classic hard rock lithologies, but also we are looking at hot sedimentary aquifers in some places. And most importantly, we want to use all the learnings from the THERMOCAL workflow to reduce uncertainty in quantification of the geothermal resources and increase the confidence in further development. So now I would like to say something about how you yourselves, how your colleagues, how people out there listening to our presentation later can engage with the project, and we really encourage and welcome engagement with the project. First of all, we have a website, and I provided the link to the website there on the left. We have a project email address, thermocal@glasgow.ac.uk, and we also have a LinkedIn page for the project, so you can follow that page, and we've started to become active as of the last few months, the last 6 months, I would say. So you're welcome to interact with any of these communication channels, and of course you can contact me and any of the THERMOCAL researchers at any time. Also, I would like to point out that we are active with webinars like this. So thank you again, Joe, for the invitation, and thank you, BGS, for the invitation, GS and I for the invitation. We are active with webinars, with paper publications, and also with presentations at national international conferences. Two that are coming up very, very soon are listed here. We're going to be at the All Energy 2026 in Glasgow in just a couple of weeks, 3 weeks. We're going to have a dedicated stand for the Glasgow Centre for Sustainable Energy, of which I'm the director, and we have planned a dedicated 1-hour spotlight session on THERMOCAL and geothermal technology. So if you happen to be in THERMOCAL, you're more than welcome to stop by. Also, we have a paper on THERMOCAL accepted for presentation at the World Geothermal Congress. So you can see that the three nations will have a presence at the global venue that the WGC represents. WGC is going to be held in Calgary, in Canada in June. And I am pretty sure that I will see some of you there. So I want to make sure that we have time for some discussions and some questions, and hopefully I will be able to answer as much as I can. So I would like to wrap up thanking you for your attention. I know there was a little bit of probably too much information in too rushed a way on a big project that brings together many people, but I really hope that this gave you a flavor for the why THERMOCAL, what we plan to do during THERMOCAL, what we expect to obtain from THERMOCAL, what THERMOCAL will not have time and resources to cover, and we are very open to integrating with other ongoing efforts with like-minded geothermalists out there. Very much needing support, not only from the existing current supporting partners, but also from any additional partners out there wanted to help us along the journey. Also very open to co-creating, co-branding opportunities for knowledge exchange. We want to support the geothermal sector. We want to see more and more and more geothermal done, not only in Scotland, in Northern Ireland and in Norway, but really throughout the world. And we feel that this is a good moment for geothermal. We think that definitely the voice of the geothermal sector is increasing. There is definitely more attention across continents to the resilience that geothermal energy could offer. It's not just about the dry thermal feasibility. The technology is actually there while we continue to refine it, of course. It's not about just the dry costs. It's about cost and benefit analysis. And we need to make sure that we are conveying this journey also to our communities, local communities, rural communities, urban communities. We can do geothermal pretty much everywhere, pretty much, depending on which form, but we need to be transparent with how we assess the potential and how we can show that we've done our best to de-risk the estimation of potentials and resources.